me maybe talk a bit about Turkish Academy of Management. Currently and recently, actually, we became the affiliate and partner of Academy of Management. And as Turkish Academy of Management, our main aim is to bring scholars, those of us work in the management field, together for usually an online and sometimes in-person platforms for exchanging ideas, developing research, and engaging with new approaches and projects together. I am the co-coordinator of the Organizational Behavior Interest Group. My name is Duysal Aşkun Çelik. I currently am working at Rice University Jones School of Business as a lecturer, and I'm also teaching at City University of New York, New York City College of Technology. And I've been, working with also industries, companies for several years myself in the field of organizational behavior and also organizational psychology. Originally a psychologist, so that's about me. And then I will talk about Ken a bit, but I also have my co-moderators, Professor Amer Al-Atwi and Professor Anindo. I will also introduce their affiliations as we move along with the questions. Today, Ken actually is going to be with us, and thank you so much, Ken. I will do a brief introduction about you, if I may, and then we will go forward first with Anindo's questions, and then we will circulate between moderators. I am the last moderator, so I'll have a few questions. In the case that you have questions apart from our questions, please save them. You can write them in the chat, but hopefully we will have some time to include those questions as well. So welcome everybody. We are very happy to see you all. There are so much to say about Professor Ken Bollen. He is the Henry Rudolph Immerwahr Distinguished Professor in the Departments of Psychology and Neuroscience and Sociology at the University of North Carolina at Chapel Hill. He is also a member of the L.L. Thurstone Psychometric Laboratory and a fellow at the Carolina Population Center. A leading expert in structural equation modeling, SEM, Bollen has published 4 books and numerous articles on the topic. He and his colleagues have developed new estimators, fit statistics, and diagnostic tools for analyzing latent variables, measurement errors, non-traditional measurement models, and flexible longitudinal models. His pioneering work in SEM has earned him prestigious awards, including Psychometric Society's Career Award for Lifetime Achievement, the Lazarfeld Award for Distinguished Contributions to Sociological Methodology, the Sells Award for Distinguished Multivariate Research, and Dr. Honoris Causa Honorary Doctorate for Uppsala University, Sweden. In recognition of his contributions, Voxing University in Hyderabad, India established a Kenneth Bollen Chaired Professorship in Structural Equation Models. Bollen is a fellow of the American Association for the Advancement of Science, the American Statistical Association, and the Association for Psychological Science. His research has been funded by NIH, NSF, USAID, the John Templeton Foundation, and other organizations. He is the author of Structural Equations with Latent Variables, 1989, Wiley, Latent Curve Models, a Structural Equation Perspective with P. Curran, 2006, Wiley, Elements of Structural Equation Models, Impress, Cambridge University Press, and editor of Testing Structural Equation Models with J.S. Long, 1993, Sage. Very recently, Bollen has been elected to be the member of the American Academy of Arts and Sciences, which honors excellence and convenes leaders from every field of human endeavor to examine new ideas, address issues of importance to the nation and the world. Ken, again, welcome. Very happy to be here with you. I don't know if you want to say a few words before we start.
Well, just a few to thank you for the invitation and the nice introduction that you gave me, and I appreciate the panel. Working on a set of questions for this. And I appreciate the people who are coming here because I know it's not the most convenient time of day for some of you. It's midday here, so that's a little bit different than what a lot of you are experiencing. So I do appreciate that. So thank you very much.
Thank you and welcome again. So Anindo, Dr. Anindo is our first moderator who is going to present his first question. But first, let me also introduce him. Dr. Anindo is Assistant Dean for Sustainable Business Research and Associate Professor of Organizational Behavior at Vauxhall University, India, and he is the esteemed member of Turkish Academy of Management, and he is having wonderful contributions to us so far. So thank you, Anindo, and welcome. And go ahead, please.
Thank you very much, Duysal, for this generous introduction. And it's so nice to meet you again, Ken, over here. And as we have a as we have a mixed crowd, and all of us may have different kinds of experiences about using quantitative methods in our own research. But one of the questions which I always used to argue about, especially one of my economist friend used to argue with me, is that why are you so fancied about this structural equation modeling? I mean, you can always use, it's something which is very similar to regression, I mean, the multiple regression method, or some people also used to say, no, it's just another kind of multivariate analysis. So I think there are many different things which go on in our minds sometimes, and we have different kinds of arguments. But it would be good, perhaps, Ken, that if you could say that what according to you is the fundamental difference between structural equation modeling and kind of the conventional regression methods that we use.
Sure. I guess the first thing I'd say is you should get a better friend. No, but seriously, this is a very common question that comes up in many situations. And one way I would describe it is that for regression analysis, that's used for a lot of different purposes. We can use regression just to describe conditional relationship between one set of variables and an outcome variable. And we can just say, well, what's the mean like if we control for this set of variables? I would see that more as a descriptive purpose, and regression is really good in that situation. Another purpose that regression might be good for is a prediction problem, where you really are not interested in anything more than just being able to predict whether some outcome occurs and at what level. And there's just well-developed procedures in regression, and they continue to develop, that work well for prediction problems. The last main purpose for regression is one that gets a little bit closer to structural equation models. And this is an explanatory purpose, where you think that some variable on the right-hand side of an equation has a influence, causes, net of the other variables that you have on that right-hand side of the equation, causes some outcome variable, and you're using regression, to develop estimates of it. Now, with structural equation models, in most applications, it often is used as a scientific tool to make causal inferences. And this is different. I said with regression, right? We've got prediction, description, that sort of thing. That's not worrying about making causal inferences from one variable or more variable on the right-hand side to the variable on the left-hand side. With structural equation models, you're trying to construct some model that represents a series of hypotheses that connect a lot of variables. And some of those variables may be what are called latent variables. And these are variables that we don't have in our data set. These are variables that, at least in our theories, our hypotheses, play some important role. But in our data set, all we have are indirect indicators of it. So as part of our model structure, we want to recognize that these variables in our data set are imperfect representations of these abstract concepts from our theories. Structural equation models, you can build structures like that. The usual application of regression is just an observed outcome variable regressed on a series of observed explanatory variables or descriptive type variables on the right-hand side of the equation. So I would say that the main difference is that you're trying to make causal inferences with structural equation models. Most of the applications of that, some of the variables are going to be latent. In other words, not even in your data set, only indirectly captured by measures you may have in your data set. And you have a technique with structural equation models that is controlling for the fact that there is a lot of measurement error in your data. I think another difference with structural equation models is that there's additional diagnostic statistics that can reveal how consistent the model structure is that you've put together and the data in your data set. Whereas with regression, you do have things like the R squared and standard errors and coefficients, that type of thing, but you don't have something that's equivalent to this summary of the whole model and how well it explains the association between a set of data. And that provides feedback on whether the structure you hypothesized is reasonable or not. So I would say those are the main differences.
Thank you so much. And Anindo, if you don't have anything to comment on Ken's response, I will move ahead with Amer's question. So let me also introduce Dr. Amer Al-Atwi. He is a professor of organizational behavior at University of Al-Qadisiyah, Iraq. Associate editor at Leadership and Organizational Development Journal, and our regional MENA at the Middle East, North Africa regional coordinator at Turkish Academy of Management. And Dr. Amer also contributes to our work in this region. So welcome. And first of all, let me introduce you to ask the second question, Amer. Go ahead, please.
Thank you so much. Thank you so much. I am very glad to be part of this session with distinguished Professor Ken Bollen. It is a wonderful opportunity to learn from his experience. My first question is about sample size requirement for structural equation modeling. How reliable is the 5 observations per item rule? Please.
Thank you, Amir, and good to meet you indirectly.
Thank you.
Yeah, this question of how large a sample size must be for structural equation models is a very common question. And unfortunately, there's not a single rule, a single answer that you can give. But let's talk about those 5 observations per item, just to illustrate some of the possible problems, with some of the rules that are out there. Let's say that we had a factor analysis, a confirmatory factor analysis, which is part of a structural equation model, where you had just 3 indicators or 3 items to measure one latent variable.
Okay.
Right? This rule would say that we need 15 cases. And 15 cases is really small. You might get lucky and it might work, but by standards of most applications, having only 15 cases would probably get you in trouble. So just that as an illustration, why that rule, may not work out so well when you're trying to plan a study. Now, I can't give you a single number, but I can give you some of the things that will affect how large the sample size has to be. There's several factors that come to mind, and one of these is how close is the model that you specified, you hypothesized, to at least an approximation to the true structure. The closer you are, the smaller the sample size you can get away with. A more pessimistic view is the further you are from the true structure, you may be getting in a lot of trouble, at smaller sample sizes. So the better the structure, the model that you hypothesize to start with, gives you a little leeway where the sample size would be a little less demanding than if it was a poor structure that you put together. Another factor that influences this is how strong are the relationships in your model. And there's a lot more than the R squared to these relationships, but this is a convenient statistic that we're familiar with. And generally, the higher the R squared you have, the smaller the sample size you can get away with. If you have really weak relationships, the R squared's, only explaining maybe 3%, 4%, 5%, it may be harder to get away with, the same size sample that it might work if that R squared was up around 0.6, or 0.7 or something of that nature. So the smaller the R squared, the bigger the sample size you need. The bigger the R squared, the smaller the sample size. The size of the model itself, this makes a difference. If you have a really large model, many latent variables, each measured with many indicators, that's going to push you in the direction of needing a much larger sample. Alternatively, if you have a relatively simple model, not that many latent variables, not that many indicators, you could get away with fewer cases, for your analysis. Another factor here is how many indicators are there per latent variable? And for this one, as long as you don't get, let me put it this way, having 3 or 4 indicators per latent variables will probably enable you to estimate a model at a smaller sample size than if you only had 2. Or in the extreme case, if you only had 1 indicator in a model. So the number of indicators per latent variable affects how big the sample size should be. Then there also is the estimator that you use for your structural equation model. Now, most of the estimators that are implemented in the standard structural equation model software are what are called either system-wide or full information estimators. And what they do is they estimate all the parameters, all the equations at once. There are alternative estimators that there are some, R packages for and things like that, some of which colleagues and I have worked on, called model implied instrumental variable estimators. And these you can estimate a single equation at a time. And they're non-iterative, so there's no question about having non-convergence, with it. So to the degree you're using this equation by equation type of estimation, you can get away with smaller sample sizes than if you're using the whole system, estimating the whole system at once. If you want rough guidelines, let's say if you're somebody analyzing surveys or something like that, and you have, 1,000 cases, most of the time you're going to be just fine. On the other hand, if you're dealing with small subjects, it's very expensive to get a subject in your study, and maybe you just have 25 people or something like that. It might work, it might not, depending on these other factors, that I was just talking about. So I can't give you a definite number, and I can't give you a rule that will work in all contexts, but those are some of the things that go into it.
Thank you so much.
Sure.
That's very clear.
Okay, thank you for
Yeah.
additional questions. And now going to Anindo. Go ahead,
Yeah,
Anindo.
I just have so whenever we are talking about structural equation model, and that's the entire webinar about, maybe it's important for us to also understand the basic difference between measurement models and structural models, maybe. So what do you think is the difference between the two and the way we treat these two different kinds of models?
Yeah, this is another good question. As I mentioned earlier when I was doing the comparison of regression and structural equation models, one of the strengths of structural equation models is that you're able to put in these abstract variables that appear in our theories, whether it's socioeconomic status or happiness, satisfaction, all of these variables that are quite abstract but are formulated in our theories. Well, we can represent those abstract variables in the structural equation models. We call them latent variables as part of the model. Now, if we want to do something with those latent variables, we have to have measures of them. We have to have some indications of their movement, how they behave. And these are the indicators in the data set, the measures in the data set that we have. The measurement model relates these latent variables to these measures we're using to gauge the magnitude of these latent variables. So the measurement model is concerned with, as the title suggests, it's a model of how the measurements occur. How do the latent variables relate to the observed variables that are serving as measures? That's the measurement model. Now, the structural model will take its focus to be how do substantively different variables influence each other? How do they relate to each other? So maybe we wanted to see how age and gender and race relate to happiness. So we're sort of focusing on those variables and what causal influence they have on happiness. When you're relating distinct substantive variables to each other, you're building a model of their relationships. I generally call that the latent variable model because you're explaining one or more latent variables. But in a lot of the literature, that's referred to as the structural models. Now, why do I resist and continue to call it latent variable model? Because I think it's an unfortunate term in that all of these relationships are structural, whether it's the latent variable to the observed variable, which is part of the measurement model, or it's distinct substantive variables related to each other. They're all structural relations, which by structural, it's generally meant causal relationships. So does that answer your question, Anindo? Yeah.
Yes, it does. In fact, there is one follow-up question which has come, I guess, on the sample size question, which was just asked that what are your views on parceling? And is it a good idea to parcel the items when sample size is small?
Yeah, that's a good question. Now, some may not know what parceling means, and what that is if you have a large number of measures to measure a single latent variable, rather than putting each individual measure as a separate indicator, you might add together. So maybe let's say you had 12 indicators of a single latent variable. Parceling would be, okay, I'm just going to take 4 of these indicators at a time, add them together, and make that be my new indicator. Parceling depends somewhat on how well studied these measures are. Because when you add them together like that to form a new measure, you're already assuming that there's no problem with those individual indicators that go into that sum. And if there is a problem, you can be masking that problem, hiding that problem when you do your analysis. It can cause you trouble. On the other hand, if you're dealing with a very well-studied scale, you yourself are pretty confident of past analyses that have been done of that, you could add them together in the case of a small sample in that you are shrinking the model in a sense, right? We said that one of the things that can influence how big the sample size is how many indicators you're trying to analyze. Well, parceling can reduce the number of indicators that you're analyzing, and it can help in that fashion.
Great. Over to you, Amer. You had a question, I guess.
Yes. Going
Yeah.
back to Amer.
Yeah, thank you. I would like to ask you about CFA using Amos. When should researchers rely on modification indices to adjust their models, and what caution should be taken?
Okay, it's another good question. Now, the modification index in statistics, they would refer to that as a Lagrangian multiplier statistic, and these appear in lots of fields of statistics. Just for historic reasons, it ended up being called the modification index in structural equation models. Personally, I would say this. I would say I think the modification index is used too much, too soon. It's what happens, very common in confirmatory factor analysis or structural equation models more generally. The first model you fit exhibits problems with fit. And too often, the first thing people do is they say, well, let me look at the modification index. And for those of you who don't know what that statistic is, it's an estimate of how much the chi-square, where the chi-square is a measure of fit of the model, how much the chi-square would be reduced if I introduced this one parameter that in the prior run was fixed to often 0. So it's saying, in a sense, it's telling you, all right, what else should you introduce in the model to improve the fit of the model? And it's looking at just one characteristic at a time. It's not looking at a group of characteristics. So to me, I often find that people know a lot more about their data and the subject matter that they're studying than they let on, in the sense that they want to just look at these statistics, which are very imperfect, rather than just sort of thinking through, well, why didn't this fit? Did I assume that there's just one latent variable in these 10 indicators, when in reality there's actually 2 latent variables? Giving a little thought, you see, well, oh, these 5 look similar to each other. They may be tapping this other concept, and these 5 seem to be tapping something else. So to me, a much more powerful and useful thing to do than the modification indexes right away is to just rethink the problem. You're getting a signal that your initial ideas that led to that model has some flaw in it. Do I have the right number of latent variables? Are there reasons to think that some of the indicators are going to continue correlating with themselves even after I control for the latent variable? Maybe the wording is very similar in those measures. Or maybe it's connoting something very similar to each other above and beyond what it's measuring there. So asking those type of questions first, trying them out, seeing if it works, I find that as a more helpful way to proceed. Now, at the same time, if you do make an honest effort to see what you could introduce just based on your subject matter knowledge, what you know about this field your data are coming from. And you've exhausted all the possibilities. Well, the modification index might help you out or be suggesting some things you hadn't considered before. The other thing I would do is that if the modification index suggests some nonsense, crazy parameter being introduced, maybe you have something from the future causing something from the past, or there's absolutely no relationship between this indicator and another latent variable that's telling you to load on it, I wouldn't do it. I would just use my subject matter knowledge. Because part of the problem with the modification index goes back to what I said a couple of minutes ago. It's seeing what single modification of the model will lead to the biggest improvement in fit if I enter it into the model. It could be that there's a combination of parameters that if you change them would give you a much better fit than these singles, and you can't see it because you're only getting a statistic that's telling you one at a time type modification. A good example of this is suppose that in reality, you fit a model with a single latent variable to 10 indicators. When in reality, you should have 2 latent variables there or 3. The modification index can't tell you that. It's working with the basic structure you have there and trying to modify that basic structure. It can't tell you introduce 2 more latent variables for those variables. So if you've exhausted everything else, okay, it might suggest some ideas to you, but it should not be the first thing you go to. It should be the last thing you go to.
Thank you.
Sure.
Okay, it's my turn. So we actually try to balance these questions with the technical and more general ones. So Anindo and I are trying to go more with the general, and then Amer is mostly forwarding technical questions. And sometimes there are some relevant questions that are in the chat. Thank you so much. And Anindo, I think you do a good job of moderating and combining those questions as well. So let me go ahead with my question. Ken, what are the assumptions that need to be satisfied before applying a SEM model?
Yeah, I would say there's a variety of assumptions that are needed. One assumption is that you're reasonably close to the true model, or a correct approximate model. Now, you're formulating a model and it's reasonably close. We know to start with that any model we choose is going to be false to some degree. So it is kind of a judgment call that this is a reasonable starting point. Other assumptions are that the functional form, the nature of the relationship between the indicators and the latent variable and between the latent variables to each other, if you're assuming a linear form, that this is a reasonable assumption, to be assuming when you formulate this model. Other assumptions are things that are common in regression analysis, where you assume the errors in your different equations have means of 0. For most estimators, you're assuming that for a given error term for a given equation, the variance is the same across people in the sample. This is called homoscedasticity in the statistical literature and econometric literature. And no autocorrelation of the errors. Now, let me tell you something that is often presented as if it's part of the assumption of structural equation models, which it is not, that your observed variables come from multivariate normal distributions. This is perhaps the least important distributional assumption to bring up, because some estimators don't require that multivariate normality or univariate or bivariate normality at all. They have their proper properties and standard errors and significance tests without making those assumptions. I mentioned the MIB two-stage least squares. That's an asymptotic distribution-free estimator. Asymptotic is just a fancy word for saying in big samples, it has these properties. What's more, even the more common estimators, like the maximum likelihood in the structural equation model packages, if you have non-normal data, all you have to do is request the robust option for standard errors and robust option for the chi-square tests. It'll correct for the potential problem with significance tests. So the key assumption is that you've got a reasonable structure relating these variables to each other, and that the functional forms you're using are accurate.
Okay, thank you. Amer, back to you.
Yeah, thank you. Please, Professor, in the case of a two-item scale,
Yeah.
what are the recommended approaches for conducting CFA? And what are the potential limitations, please?
Sure, it's a good question, because you find a lot of advice in the literature about the minimum number of items that you need when you're applying structural equation models. Let me just answer that one too, because there's such widespread misunderstanding about how many indicators do you need per latent variable in order to estimate a structural equation model. And the answer is it can be as small as 0, which is odd because you can do higher order factor analysis where you have a latent, more abstract factor that's influencing what are called first order factors. And that higher order factor has 0 indicators. It's using those other latent variables in order to gauge its magnitude. So the first clarification is that you will find, even by people, good scientists in this area, saying, well, you need at least 2, or you need at least 1, or you need at least 3. Point of fact is you can actually, in some models, have none, and it will still work. But let me go back to your question on 2 indicators. If all you have is a single factor with 2 measures, you got to make some strong assumptions to even estimate that model. And by strong assumptions, I mean you've got to, the most common assumption would be that the factor loading, or the coefficient going from the latent variable to each of those 2 indicators, is the same magnitude. If you don't assume that, the model will be what's called under-identified. It won't be possible to come up with a way of deriving a parameter estimate, even if you had near population data. So that's required. The situation is a little better if you have 2 latent variables, each measured with 2 indicators. That model will be identified without forcing the factor loadings to be equal. And you actually will have a way of assessing the fit of that model, a chi-square test statistic. So, yeah, you can do it. The best thing is first thing, look at rules of identification. There's lots of rules of identification out there that tell you, for factor analysis, when a model will be identified or not. If you find out that your model's not identified, then you've got to go back and replan things to develop more indicators for it. If you find that it is identified, but you're not happy that you only have 2 indicators for each of these latent variables, estimate the model, see what happens. If you think that this is a reasonable structure, just do it. And it's either going to work or not. And if it works, the results are either going to make sense or not. So I would just experiment in that way. First, though, check if it's identified, because if it's not identified, it may be very confusing to you what these results are. If you know the model's identified, you can rule that out as a possibility if you encounter any problems in the estimation.
Much appreciated.
There's a quick question, follow-up question to this, Ken. It's about CF.
Yes.
So one of the person has asked that how do you deal with common method bias in structural equation modeling?
How do you deal with it?
CFA. Basically, how do you deal with common method bias in structural equation modeling, or in, let's say, what would be some of the CFA markers? This is a question which I started. Yeah.
What I often do is, if I have good reasons to suspect that there is a methodology that's used that's influencing a subset of the indicators in common, I'll construct a latent variable that is tied to this methodological issue, and I'll let it influence each of my indicators. And I'll estimate the model to see if there's evidence to support that hypothesis. So I would just construct a model reflecting that common method bias so that some indicators will be measuring both the intended latent variable, the subject from the subject matter, but that indicator will also be measuring the common method that it shares with other indicators.
Thank you. Over to you, Duysal.
Okay, so since we are talking about latent variables quite often, what are the common mistakes that researchers make when constructing latent variables, according to you?
Not thinking it through. Just saying, let's say you have in your data set, you have race, gender, age, and you try to construct a latent variable that's demographics. That's not going to hold together. These are distinct variables that often are important in our analysis, but there's no reason to think that they are a measure of some abstract variable that are demographics. So I think there's sort of a not thinking it through, and a lack of systematic thinking about each of the latent variables. Ideally what you should do is you should see what the major abstract variables are in your data set. For each of those abstract variables, provide what's called a theoretical definition. Explain what the meaning is, as you intended, for that latent variable. And that definition, although it's often skipped and not done in many applications, that definition is so important because if you look at that definition, it's going to tell you how many dimensions, how many distinct parts are there to this concept. And it's also going to provide a standard by which you can choose your indicators. So you have that definition there, and you have these indicators in your data set, and you can compare. You can say, well, I was thinking of using this to measure self-satisfaction. Well, give your definition of self-satisfaction. Look at this indicator and ask yourself honestly, does this seem to correspond to this definition that I just gave? And go to the next indicator, do the same thing. Or if you're in the fortunate situation where you can construct your own measures, it provides guidance on what are reasonable, indicators to construct, to tap into that measure. So I would say the most common problem I've seen is a lack of good conceptual background work in these. Too much of a hurry to just say, well, I'm going to group these variables, I'm going to group these variables, I'm going to, put it into a latent variable model and see what it looks like. You might get
Thank you.
lucky. Most of the time I've seen it, people are not. They're just going to have a mess.
Thank you.
Sure.
Amer, back to you.
Yeah, thank you. Another technical question. Please, when should researchers prefer a variance-based approach, for example, smart PLS, versus a covariance-based approach, for example, AMOS in SEM, please?
Yeah, this is a division that's made mostly by the people who work with variance-based approaches. So I really don't think much about, covariance-based approach because I'm dealing with means and intercepts. I'm dealing with one equation, at a time in some of my estimators. So I think it's almost a false dichotomy there. So the classification, although quite common and mostly coming from, I would say, the variance-based approach, there's a separation there. Now, what is said in some of the literature, this goes back to my earlier comments on normality. A lot of the literature in variance-based claims that structural equation, the more classic structural equation models assumes normality, and that PLS is an improvement because it's not assuming normality. There's a couple problems with that. One, as I explained before, it depends on the estimator that you're using in structural equation models as to whether it was developed based on a normality assumption or not. But second of all, the only thing it affects are significance tests. If you have non-normal, and we have corrections for non-normality. So that claim doesn't carry a lot of weight with me because for a long time, and I'm not talking about this as something new in the last 5 years. If I had to add up the years, it'd be a long time, 20, 30, 40 years. We've known and we have these corrective procedures, even for the traditional maximum likelihood estimator in these SEM packages. The other time where the variance base is sometimes suggested as an approach is as an exploratory tool. So if you're not quite sure what the structure is, and I'm not aware of good systematic comparisons of how a classic, SEM approach versus a PLS performs in a situation where you start with the wrong model and you're just sort of exploring different structures to see which works better or not. So that's sometimes given as a reason, and I've not seen a lot of evidence on that. One part with the PLS, there are generally when you estimate models, you would like the coefficients that you estimate to converge on the true coefficient as the sample size gets really large. That's called consistency of the estimator. Several of the PLS algorithms, and you can't guarantee that property. However, there are some nice improvements where you have a correction to make this estimator consistent, and that is available in some of the packages. So that's an improvement. Finally, I've mentioned this sort of single equation approach that I take, and I find that works quite well where you don't have to estimate the whole system at once, so there's no issue with convergence. It's non-iterative. It's asymptotically distribution free, and you get individual equation by equation chi-square statistics. So for those of you that are using structural equation model packages, you get a chi-square statistic for the whole system, This other approach allows you to get a chi-square for each over-identified equation, and this can sometimes help you pin down where problems are with the fit. So I don't know if that fully, I mean, Amir, do you want to tell me a situation where you think it might be better? And I could sort of react to that, because I'm not totally clear on whether one would uniformly, that would be better than the other.
That's very helpful.
Okay.
Okay, back to you, Anindo. Thank you.
Yeah, I think because let us ask one fundamental question once again, because we are talking so much about the nuances. So what do you think makes a good measurement model? And I mean, how is it different from a weak one in a way?
Part of it is if you look, right, so I think a good measurement model is accompanied, and this goes back to one of the earlier answers. Good measurement model is accompanied by a definition of each of the things you're trying to measure. And then with that definition, and just to be clear, I'm not saying that I'm looking for a true definition, because who knows what that is. I'm just looking at what has guided the researcher in constructing this model and selecting these measures. So good definitions for each of the latent variables in the model. That's what I would look for. Then I would look at the indicators and whether they seem to correspond to that definition, in the that was given for each latent variable. And if I find some of these indicators don't seem to correspond at all to this definition, that makes me wonder, why that was done. So I would see that as a type of weakness without explanation. And of course, we have lots of statistics to assess the fit of a model as a whole. So it is quite possible that you may have a nice definition. You may have chosen indicators that seem to correspond to that latent variable. But when it comes to estimating it with data, you're getting indications that there's something really wrong, So I would want something that fit well as these other characteristics.
Yeah, I think I would ask the fit indices question next, but before that, Amer, you have a question, I guess.
Thank you. Please, Professor, can structural equation modeling be used for longitudinal data or multi-group comparisons?
Yes, it has some excellent features in both those areas. In longitudinal models, colleagues and I, as well as many others in the field, have built lots of structural equation model versions of well-established models, but in addition, new models that are more general in nature and that enable you to test which of these longitudinal models have the best fit to the data. One thing that affects current practice now is that when we have people doing longitudinal analyses in articles, quite often the model they choose has little to do with scientific reasons. It's more to do with what they know, what's most common in their particular field of research. And it may not be the best model. And that matters because it could change some of the key parameter estimates that you have, depending on which model you choose. So there's just a ton of longitudinal models out there, give you a lot of flexibility. And when coupled with some of the fit statistics and diagnostics we have from SEM, it works really well. Multiple group comparisons. This is another very nice feature of structural equation models. If you're used to comparing groups in regression type methods, maybe you put a dummy variable in to see if there's a difference in the intercept or not, and maybe you interact that with some explanatory variables to see if there's a difference in slopes. This multiple group analysis allows you to test differences in any of the parameters that are in your model. It could be the variance of the latent variable. It could be the error variance. It could be whether the measurement models seem to be equivalent in the different groups or not. There was a really interesting dissertation that one of my students just finished up, where in America we have two major parties, are the Democrats and the Republicans. He actually did a multiple group analysis on some common attitudes toward issues, in society. And he found that the relationship between the latent variable and the responses to those indicators differed for a lot of these issues between Republicans and Democrats, which means that they're actually interpreting these questions in a different way in their relationship. When we see comparisons drawn between these two groups, say, people are just assuming that whoever you're asking these questions of is responding in the same way. So, it's sort of a fascinating application on a very contemporary issue, at least here. And I guess I would say more widespread than that from what I read in the news. So yes, you can do multiple group comparisons, and any parameter you can imagine, you can test whether it's equal or not just the usual comparing an intercept difference and comparing a slope difference. And with latent variables as well as observed variables.
Thank you.
Mm-hmm.
Okay, go ahead, Anindo.
Yeah, so this question is about fit indices. So what fit indices are most important when evaluating a structural equation model, and why?
Yeah, another good question, and one where there's a lot of controversy about it. Certainly, one of the most basic measures of fit in structural equation models is what's called a chi-square test statistic. And the chi-square compares the fit of your hypothesized model that the researcher, has estimated to a saturated model that has as many parameters as there are data points available to analyze. Ideally, what you'd like is your model, which has fewer parameters, to fit as well as that saturated model. So this chi-square measures the discrepancy between your model and that one that has as many parameters as there are data points to work with. So that chi-square test statistic is a very important one. The main drawback of it is that if you have a really large sample, it has tremendous statistical power. And this means that you can detect even minor problems with your model. So it could be that you have some tiny omitted covariances of two errors. Maybe it's a correlation of 0.001, which in practical terms you would say, well, that's ignorable. But if you have a big enough sample size, the chi-square will be able to pick that up and it will reject that null hypothesis. So what you have for decades now are people proposing alternative ways to measure the discrepancy between your data and the data predicted by your model. And so with these fit indices, there's a wide variety of them. One that I find particularly helpful, particularly based on some simulations colleagues and I have done, is just the BIC. We find that this does a good job of discriminating between models, and it has reasonable statistical background based on what's called Bayes factors, comparing Bayes factors. I calculate this in a different way than the packages do, so that when this BIC comes out negative, that's evidence in favor of your model. If it comes out positive, it's evidence against your model. And if it comes out 0, it's neither, supportive or not with the saturated model. Other fit indices that are out there, which I think can be helpful, something called the relative non-centrality index. This was something proposed in 1990. I think it was Psychological Bulletin still then, if not Psychological Methods. And this is related to the more widely used comparative fit index, the CFI, which appears in most SEM packages. The main difference of the relative non-centrality index and the CFI is that they're equal as long as the relative non-centrality index is 1 or lower. But if the relative non-centrality index is greater than 1, the comparative fit index is forced to be 1. I don't think that's a good decision. I like to know how much above 1 it is because it provides a diagnostic for me. But comparative fit index, CFI, which is widely available, and the relative non-centrality index, they will be identical as long as it's 1 or less. They only depart when it's greater than 1. The Tucker-Lewis index, this goes way back to 1973 in Psychometrica. This is another fit index that, like the relative non-centrality index and comparative fit index, one is representing ideal fit. In practice, if you fall below 0.9, people will question the structure of your model for both this Tucker-Lewis index and this comparative fit index. Another one that's popular is called the root mean squared error of approximation, RMSEA. This one is scored in the opposite way, so that the closer to 0, the better the fit. And if you get above 0.1, people would raise questions about your model structure. So that's one that's quite popular, though I would urge caution using that RMSEA when you have not that large a sample. It tends to be a bit too, those standards tend to be a bit too rigorous to be acceptable. Now, there's many other fit indices that are out there. To some degree, there's a variety of mixes that you could use, but what I would point out as the most important is don't just report one of those fit indices, because they vary in what they're measuring. And if I'm a review and I see somebody just report one fit index, I'm wondering, did they just select the best, this group of measures, to present their model in their best light? This is why if you have a variety of fit indices, they're tapping slightly different things. And if they all consistently are saying this is a good fitting model, I feel reassured. If it's a more mixed picture, I worry a bit more. And maybe I'm going to look into modifications of the model.
Thank you.
Quick follow-up question. Quick follow-up. That is, one of the audience members have asked that the newer robust fit indices are sometimes worse than the old ones. And when you are using the triplet like RMSEA or CFI and SRMR, there is always one that doesn't fit. So what is your opinion on this, and how do we deal with this mismatch here?
Yeah, that's a good question. I think key is understanding some of the properties of the fit indices. So, for example, suppose that the BIC, the BIC, the CFI, and the Tucker-Lewis index all look good, but the RMSEA is higher than you're expecting and pointing to a problem. Well, I know from the simulation work that colleagues and I have done that if I'm dealing with a smaller sample, I'm going to downweight the RMSEA in my assessment. Because in the simulations we did, we had something like, I think it was 75 or 100 cases, and we estimated the true model, absolutely no error in the model. And using the usual standards with the RMSEA, we were rejecting like 40% of the models that we knew were true. And the RMSEA tends to like what we considered highly misspecified models if the sample is really big. So if the sample is really big, even with serious problems, the RMSEA may come in pointing you toward keeping, that model. So knowing a bit about the properties of those fit indices can be very helpful in assessing whether you should just dismiss what was occurring there or pay more attention to it.
Amer?
Yeah. Something many researchers ask is what best practices should researchers follow when reporting SEM results?
Yeah, and it's another good question. And there are, I wish I could remember the exact citations, but I can't. There might be one in the very nice handbook of structural equation models edited by Rick Coyle. That may have a chapter on reporting structural equation models. So that could provide some guidance on that. But certainly, some of the things I would want to provide are similar to any statistical analysis, where you want to know the source of the data, the nature of the sample. Is it a probability sample or a non-probability sample? That's being analyzed. The journals probably wouldn't let you do too much on descriptive statistics, but you certainly want to know about the descriptive statistics to make sure there's nothing that's showing up that appears odd to it. But when it comes to the specific structural equation model itself, here too, you're going to have to come up with some type of compromise between what you want to do and what the journal will allow you to do for space considerations. Because there's so much statistical information provided in structural equation models, you can't report all of it. So some of the things which would be great to save are the data set and any modifications that you made to it, so that others could reproduce your results. The input code and the output code that you have as supplemental material. In the actual article, you can present key coefficients. It could be that a lot of your focus is just on whether this latent variable L1 has an effect on this latent variable L2. You definitely want to have that coefficient in a table somewhere or in a figure with a standard error, so that you could gauge how its statistical significance as well as its magnitude. The R square for the equations, how much variance is explained in those equations would be important. The fit statistics that we were just talking about, having a table that's reporting chi-square, degrees of freedom, p-value for that chi-square, a variety of these fit indices, at least 3 or 4 of them that are widely used. I would want to see that. So some of it, I guess that it's really sort of a 2-part answer here. One part is the same thing you report for any statistical analysis. Basic background information, how much missing data there is, what you did with the missing data, et cetera, et cetera. And then the part that is specific to the SEM, you're going to have to make some sensible choices what is most central to this article where the user would want to see it? Because you can't, like if you have a moderate sized model that has a bunch of latent variables and indicators, you know, most of your article would be these tables presenting relationships between the latent variable and the indicators, you know, this, that, and the other, which may not be of central interest. It might be most interest is focused on how these latent variables are related to each other. So I would choose tables that corresponded to the more central part of your arguments in the article and have supplemental material. You know, often journals now have places where you can have material to accompany your article that interested readers can go look at. So I don't know if that, if you have any follow-up on that, or if I didn't cover something you were particularly looking for.
Thank you.
No, I guess that answers I pretty sure. Over to you, Duysal.
Okay, thank you. And I'm going to include one also comment, one question also from the chat. So what are the most commonly used software tools for SEM in social sciences and how do they compare? And then one of our participants also asked, with the advent of the AI, e.g. ChatGPT, how one can use SEM seamlessly. So I just wanted to combine these two since we were talking about tools.
Well, let me tackle the first one and then get a little more clarification of the second. So the most commonly used ones to date right now, I would say well, right, so I'm mostly dealing with what I encounter in the States, right? So it may be different in other places, but in the States, I would say that Lavaan, which is an R package, Lavaan, is growing in importance and quite a nice package. And the second one that's really comprehensive is M+. M+ is a commercial package, so it's, you know, subscription based. Lavaan is an R package, so, you know, part of its widespread use, I think, is that this is affordable, you know, by most people. So those are two widely used. There are still users of course, of Listro. There's which was one of the original packages. Still some users of EQS. Amos came up already. That's still available and being used. There are actually many packages, but really today I would say in the States, M+ and Lavaan are the dominant ones. Now the second one had to do with AI. Can you ask me again what the question was?
Sure. With the advent of AI, like ChatGPT and all, how one can use SEM seamlessly. So is SEM incorporated into the AI application so far?
I've not seen them combined. It certainly seems like this could be. There are people that have written programs. So M+ kind of goes like one model at a time. There are people that have written programs that you can run multiple M+ programs, you know, with just one input type thing. But that's a little bit different than sort of AI based. It could be out there, but I'm not aware of something that's widely used and that I've heard, you know, really good things about. So it seems quite likely, you know, if it's not out there already. But it can be a danger. I mean, there was I suppose you could call it an early version of an AI-like function that was called the automatic modification index. And what would happen, this was with Listro, and this was, I would say, 25 years ago, something like that, maybe longer. what you would do is you would estimate your initial model. Then it would use that modification index we were talking about to automatically choose what would give me the best improvement in model fit if I loosened it up. And then it would go to the next one, the next one, next one, next one. And it would just keep doing that until you had a model that seemed to describe the data well. But people just found, without any kind of human control, you got a lot of nonsense type model structures, that were proposed with that. So it would have to be a really good AI program that knew the field as well as these programs to know what type of modifications to make.
Okay, thank you. So
Amer?
final questions. Anindo? No, first Amer and then Anindo.
Amer will go first, yeah.
No problem.
First Amer, go ahead.
Anindo or Amir?
Amer, you go ahead.
Yeah. How is mediation or moderation test in structural equation modeling?
Yeah, right, so two different things here, right? So mediation is whether part of the effect of one variable on another is transmitted through another one or more variables. And the moderation is looking at whether a combination of values of variables has an effect above and beyond just the straight linear effect. Both of these have a long history in structural equation models. You could argue that structural equation models, was the first kind of systematic approach to mediation. And the way it's done, the way it was recommended in the past, had an elaborate series of steps, but I don't think that's needed. I think formulate your model. This is for mediation now. And once you estimate your model, Levon as well as M+, have programmed in algorithms that I and other people have developed to talk about what are mediated effects and what are their statistical significance. So it's automatically provided to you. So it's relatively straightforward in the widely used packages. I would say the area that is still being developed, but there's a long history behind it, is what happens when some of the variables that are mediators or outcome variables are not are categorical, and so there's a lot of work being done on that is out there. And on that score, there's also alternative approach, which is kind of the potential outcome literature and DAGS literature, talking about mediation effects and defining different aspects of mediation in that context. Now, for moderation, if you're just dealing with observed variables, the moderation is very much like it is in regression. It's not that different. You define a new variable that's perhaps a multiplicative combination of variables or some other form, and you study what its impact is. You naturally have to take account that these relationships are nonlinear, so you can't interpret the components involved in the moderation as if they are just separate effects that are the same regardless of the magnitude of the other variable. But there's also, and this has been true for 20, almost 30 years now, a lot of work on what happens if you have interactions of latent variables. So you have variables that are measured with error, but you want to look at how their combination of values are there. And we have a variety of different estimators for that purpose, and still a lot of literature looking at when one approach versus another functions best. So lots of options.
Thank you. Anindo?
Yeah, just a quick follow-up. One question has come that in mediation and moderation analysis, would you use Amos, or would you prefer to use process macro? Do you have any preference for any one of these two?
Amos, I'm not sure how Amos handles the interactions now. I'm not sure which algorithm it uses, because there's a lot of different ways you can do it. So I can't really answer that. The process algorithm, I'm not sure what's included in that, but I find that the Bond and M plus are quite good for a large class of models. And when you get to categorical variables being involved, then it becomes a little different. It's still, I would characterize it as still a lot of good proposals, but still emerging as to what's the best way, to approach that.
My last question is, how do you handle missing data in structural equation modeling or SEM analysis?
Yeah, this is something that is a real nice feature of the usual many structural equation modeling packages. There's actually two ways you can do it. One, you probably have heard of multiple imputation, where you impute multiple data sets and reanalyze the same model with them and then combine the features of them. So the multiple imputation is certainly available for it. But there's another approach, which is sometimes called FIML, full information maximum likelihood, in structural equation models. Sometimes that same procedure is called direct maximum likelihood, or case-wise maximum likelihood. But what it does is it just estimates your model without any imputations. It just takes whatever variables are available for a particular case and uses a maximum likelihood algorithm to develop the estimates without imputations. Both multiple imputation and the maximum likelihood rely on the same assumption of the type of missing data. Both those algorithms work when data are missing completely at random, or what's called missing at random. These are not my terms. These are terms that are in the literature. If you looked at the missing data literature, hopefully they make some sense to you. But the missing at random is the most flexible of the two, and thereby a little bit more realistic than the missing completely at random. And so you have those two very nice alternatives. And there's variants of each of them. Sometimes for both of these, you can include what are called auxiliary variables to make that assumption of missing at random more plausible. So that's quite nice for both of them too. So real nice features on that in SEM software.
Okay, over to you, Duysal.
Okay, well, this has been really wonderful. Thank you, Ken.
Quite well.
That was very extensive and very explanatory. I think everybody benefited from this so much, and everyone who listens to the recording will. My final probably question would be, what are some concluding remarks, suggestions, advice that you might have for researchers using SEM in their research? Thank you.
You're quite welcome. Sure. I guess just a few remarks. I don't know, I had put together some material here, but let me just mention a few things on this. Number one on my list, know the area that you're trying to estimate your model for. This is not a type of procedure where you just say, here's my data set, tell me how many dimensions there are to this thing or how many factors exist. This is very demanding substantively. You can't do this if you don't know anything about the area, the subject matter. So take advantage of yours and other subject matter expertise to build your models. Ask yourself, do the assumed causal connections you're putting there make substantive sense, considering what people are doing in the field? Does your research design, now research design really is important to the plausibility of the assumptions you're going to be making here, the causal assumptions in your model. Does your research design permit you to rule out some relationships? In that ideal situation with a randomized experiment, you're randomizing effects of confounders, which is really nice. But maybe there's temporal lags, which are going to enable you to rule out some relationships over others. Another part of this, I would say, is that a lot of our areas are not that developed. So you could construct 3 or 4 different models that are plausible. We're in the habit of just going with one model. I think it would be better if you really think there's 3 or 4 structures that make sense and might work, do it. And just let the data tell you which seems to be the most consistent among those 3 or 4 models you constructed. Second, check the identification status of your model. If your model is under-identified, you're asking for trouble. So you want to make sure that it's possible, even under ideal conditions, to get the parameters that you're seeking. Third, I would say choose estimators that are appropriate to your model and your data. If you have a lot of dichotomous ordinal variables that are part of your data set you want to analyze, this is going to require a different set of procedures than the classic structural equation models. There's methods for it. I'm not saying there's not methods for it, but you can't, you might not be successful if you just treat them like they're continuous. Sometimes that will work, but sometimes it will get you in trouble. Then you should decide, am I going to try to estimate all equations and all parameters at once, as is true with most of the SEM software? Or do I want to estimate one equation at a time? I'm particularly interested in these 2 equations. The rest of them I'm less interested in. Well, there's different estimators that you could use for that purpose. Check what distributional assumptions there are for the variables. And this distributional assumption, I'm only talking about this because we're talking about choosing estimators. This is where the distributional assumption comes in. Distributional assumptions are not an inherent part of the structure of the model you're setting up. And so see what they are. There's some estimators that will be large sample distribution free, like I mentioned, that mid 2/6 least squares. The maximum likelihood, that's developed on normality assumptions, but there's corrected procedures if you have non-normal data, and you should use those corrected procedures. Then it would just be a matter of estimating the model and then assessing the model fit. Now, what is often overlooked in estimating the model fit, this next step, is odd results. Are the signs of these coefficients in the direction that would be predicted by subject matter experts and in past studies? Are there any variances that are estimated to be negative or correlations estimated to be greater than 1? These are called improper solutions. We know these are impossible in the population. You can't have negative variance and you can't have correlations greater than 1. But in the sample, they might occur. And you want to see if you've got issues with that. Then look at the fit statistics, over-identification tests. There are the system-wide maximum likelihood that are available in the standard packages. There's also equation-by-equation fit statistics, chi-squares, that are available. I told you a set that I think are pretty good is that chi-square test, the BIC, the relative non-centrality index, or its similar CFI, the Tucker-Lewis index, and the RMSEA. And so assess those. Now, a lot of the time, you're going to find that one or more of these assessments of fit are pointing to problems. So then what happens is you got to go into what's called a re-specification stage. This means it's a fancy name for changing your model, modifying your model. And when you take that step, you have to recognize that you've now become more exploratory than confirmatory, or you're heading in the exploratory data analysis. You've got to be a little distrustful of your p-values and the rest of it. But given how much trouble it is to get data on some of these things, I wouldn't just stop and say, well, that's it. My thing didn't work out. I'd try different specifications, but let people know that you're reacting to some initial results. Don't pretend that whatever model you end up with at the end is where you started. So those would be rough guidelines that I would provide.
Thank you so much. I mean, so grateful to have you today with us, Ken. I think everybody had a really, good understanding, and I'm getting a lot of reactions, positive reactions from this webinar. Thank you everyone for joining this session hosted by Turkish Academy of Management, Organizational Behavior Interest Group. And very thankful and appreciative of Ken Bollen's presentation today. And Ken, looking forward to see you again, maybe sometime with maybe new questions, new set of questions, who knows. And thank you to my moderators, Anindo and Amer, preparing this. It's been actually many months before this we've been preparing. So it took some time and it took some energy and effort on the part of us and also Ken we got back and forth to actually prepare the questions to make the latest list. So thank you for all the chat messages as well. We are looking forward to the next event, and stay tuned. We'll be in touch. The recording will be there. So those of you who couldn't join or maybe couldn't stay for the whole session can go back and listen to the recording. So we'll say goodbye for now and see you again. Thank you.
Thank you so much.
Thank you.
Thank you.
Thank you.